better be Gryffindor!
So my project is trying to create a Harry Potter sorting hat. And why a sorting hat? Well, it takes in an input of a wizard or a witch and a bunch of information about them by being on their head, which are some random variable inputs. And it returns a house that they're in. And this is just the most likely house based on the inputs. There are 4 houses that people can be in. So this is a classic example of a classification task. And there is an online website called Pottermore.com where people can actually learn their own house. And the hat, like the algorithm is designed by J.K. Rowling herself. So it's probably like very, very accurate because who else knows the algorithm better than the person who wrote the books? And yeah, this is an example of a house you could get sorted on the website. But I wanted to investigate, firstly, how much do people agree with the house that they're given on Pottermore? And can I build something with a similar or equal accuracy? So what I did was I created a form. The form asked what house people are in and whether they agreed with the house that they were in, and some questions about their values. Why their values? I think that the values are a really good predictor of what house people are in, just by the way that the sorting hat in the first scene took into consideration Harry's desire to not be in Gryffindor because it reflected a value that maybe he didn't want to be seen as someone who was very ambitious or cunning. And that's why I think that the values are a really good capture of the things that make up our Harry Potter houses. And I used the ESS Human Values scale by a psychologist called something Schwartz. And it just asks you a bunch of questions about your values and how much you agree with them. And it gives you a breakdown. And I went around interviewing a bunch of people at Stanford in the rain with my form. And I got 70 responses. And for out of those, 49 people did the Pottermore quiz and 32% actually agreed with their house, which was 65%. And I feel like we could do a little bit better. And I also made a covariance graph of all the houses, of all the questions I asked, and how they correlated. Sorry, this is a correlation constant, how they correlated with the other questions. And the most related questions happened to be these. And I was honestly a little bit surprised by how weak all these relationships were. But I did find that this question, which there is a high correlation between people who like surprises and who like to take risks, which was very, very interesting. If you're curious, you can also explore the other correlations. Honestly, this was a very ambitious project. I didn't have enough time with it, and I ran into a lot of problems. A lot of my data wasn't usable, and I learned that I have to collect way more data. I also learned that there was very weak correlations between questions that were basically asking the same thing, which was highly concerning because it meant that people weren't paying attention. I don't know what was happening, but I'm gonna have to think over that next time I do the study. And I don't think I sampled that big of a group of people. I think I might have just selected from my friends or people who were nearby me on campus. So that's another thing I'm gonna have to think about. And I also ran into a bunch of errors with code when I was trying to code this up. So I guess what I'm gonna do is give you an explanation for what I would have liked to done if I was better at coding. And here's the explanation. So there's a lot of differences between the binary classifier that we learned before and the multivariable classifier that the sorting hat is trying to do. So it took in binary inputs and returned binary values. So it could ask questions like, do you like chocolate? Do you like candy? Do you like ice cream? And output, do you like pasta? Yes or no. So very simple, binary in, binary out. The multivariable classifier that I tried to build took in an array of people's scores of how much they believed in certain values. So it'd be 0 would be I don't believe in this at all. And 6 is I strongly believe into this. And it would output based on those values, how likely people, which house they're in, right? And that's either Gryffindor, Hufflepuff, Slytherin, or Ravenclaw. So that's one of 4 options. So the difference is we have binary inputs and binary outputs. And in the multivariable sorting hat classifier, we have not binary inputs and not binary outputs. And I actually realized the not binary inputs weren't a huge problem. It was really just the outputs that were a huge problem. So before we talk about how we solve for this problem, let's talk about the training data. The training data consists of 2 parts. It consists of a vector of people's scores and how much they agree with it, and then a vector showing which class that they've been sorted into. So for example, if someone was sorted into Slytherin, like this person has been, they would have 0, 1, 0, 0, as you can see. And if they were sorted into Hufflepuff, they would have 0, 0, 1, 0. Hopefully it makes intuitive sense how this data can be organized. And the next thing we have to do is calculate the likelihood of one person's data, which is the probability that the person has the values that they have, given that they are in the house that they are classified into. So what is the probability that they are very, very ambitious and care a lot about the environment, for example, given that they are a Slytherin? And then what we can do is calculate the likelihood of all data. So we can go through each person and their values in their house and multiply that by each other's to get the likelihood of seeing all of this data. But how do we break this down? How do we actually figure this out? Imagine that we have 4 classifiers, right? A different classifier that calculates a different Z value for a different house. And then it outputs the probability of us being in that house based on the Z value. And the key thing to note is that each of these classifiers assign different weights to the answers coming to the different questions. So for example, and this kind of makes intuitive sense, right? Maybe someone from Slytherin would assign a higher value to the question about ambition or, being like very like self-driven as compared to someone from Hufflepuff who might weigh it negatively. So therefore, it actually makes a lot of sense why these different weights and different numbers might appear for different classes. And what we can note is that the different weights themselves can be classified in an array called weights of Slytherin or weights of Ravenclaw or weights of Hufflepuff. So yeah, that's just notation. So the Z value for each specific house can be calculated as the weight of that house, the weight array of that house transposed times X, which is the vector of the people's values. And then how do we go from Z value to probability? Obviously, our sigmoid function no longer works. So we're going to need a new function. And the new function comes in the way of the softmax function. So what we do is we do e to the power of Z of that specific house over the sum of all the e to the power of Z's. So the probability of Slytherin is going to be e to the Z value of Slytherin over e to the Z of Hufflepuff, Ravenclaw, Gryffindor, etc. And that's how you can hopefully see all the probabilities also add up to 1. That's super cool. How do we represent this in a differentiable form? Recall that earlier we represented our classes in this format, where we had 0s in the class that it wasn't allocated to and 1 in the class that it was allocated to. So what we're essentially doing, oh, sorry, I don't know why that happened. Yeah, what we're essentially doing is we're saying that the probability of your X being the X that it is, given the house, is the multiple of something over all 4 houses. And this looks a little mathy, but let me break it down. It's essentially e to the power of Z Gryffindor to the 0th power, corresponding with this, e to the power of Z Slytherin to the 1st power, corresponding with this, oopsie, corresponding with the 1, and then e to the power, and then 0s everywhere else. And what ends up happening is only this value gets counted. And that is going to give us, so this equation ends up giving us the probability that your person is in the house that they are by this really fun function that they have. And now all that's left to do is calculate the overall likelihood function. So we can do this through all of our people. So we can just go through, we can calculate the probability for one person and multiply that for all of our people going from x1 to xn being classified from t1 to tn. Now all that's left to do is to maximize log likelihood. And this function is differentiable with respect to thetas and the weights, and you can use gradient descent to work it out. And I didn't have time to figure out how to differentiate it, but it is possible to differentiate it. And if I had more time, I would have.